Hello everyone, welcome back to Code Lane. In today's video, I will be discussing Kruskal's algorithm, which is one of the most important algorithms in graph theories in data structures and algorithms. When we work with networks, roads, communication systems, and many other connected structures, we often face a common problem. We need to connect different locations or devices while spending the least possible amount of money or resources. This is exactly where Kruskal's algorithm becomes useful. Kruskal's algorithm helps us find the minimum spanning tree of a graph. In simple words, it helps us connect all points together using the minimum possible cost while avoiding unnecessary connections. Throughout this presentation, I will explain the basic concepts needed to understand the algorithm, the working process of the algorithm, a complete example, its advantages, disadvantages, and applications. So, let's begin by first understanding what a graph is. Before learning Kruskal's algorithm, we must first understand graphs because the algorithm works on graphs. A graph is a nonlinear data structure consisting of vertices and edges. Vertices are also known as nodes. These represent objects or locations. Edges represent connections between those objects. For an example, if we consider a social media platform, each user can be represented as a vertex, while friendships between users can be represented as edges. Similarly, in a road network, cities can be represented as vertices and roads connecting them can be represented as edges. Graphs are extremely important in computer science because many real-world problems can be represented using graphs. For an example, GPS navigation systems are used to find routes between locations. Computer networks use graphs to represent devices and connections. Airline route maps can also be represented using graphs where airports are nodes and flights are edges. Because graphs are used in so many areas, many algorithms have been developed to solve graph-related problems. Kruskal's algorithm is one of those algorithms. Now let's move to the concept of a weighted graph. A weighted graph is simply a graph where each edge has a numerical value attached to it. This numerical value is called a weight. The weight usually represents some type of cost. Depending on the application, the weight can mean different things. For an example, if we are connecting cities, the weight may represent the distance between cities. If we are building a communication network, the weight may represent the installation cost of cables. In transportation systems, the weight may represent travel time. In computer networks, it may represent the cost of transmitting data. The presence of weights help us compare different connections and determine which connections are more efficient. Kruskal's algorithm uses these weights to decide which edges should be selected first. The algorithm always prefers edges with the smaller weights because its goal is to minimum the total cost of the net. Now that we understood graphs and weighted graphs, we can move to the concept of a spanning tree. A spanning tree is a subgraph that includes all the vertices of the original graph while maintaining connectivity. In simple terms, a spanning tree connects every node in the graph. However, there is one important condition. A spanning tree must not contain any cycles. A cycle occurs when we can start at one vertex, travel through a path, and return to the starting point. Cycles create unnecessary connections. For an example, If we already have a path connecting two locations, adding another connection that creates a loop may increase the overall cost without providing additional benefits. Therefore, spanning trees remove unnecessary edges while keeping all vertices connected. A spanning tree for a graph with n vertices always contains exactly n-1 edges. This property helps reduce redundancy and improve efficiency. Now let's understand the main concept behind Kruskal's algorithm, which is the minimum spanning tree. A graph can have many possible spanning trees. Each spanning tree may use different edges. Because different edges have different weights, each spanning tree may have a different total cost. Among all possible spanning trees, the one with the smallest total weight is called the minimum spanning tree or MST. The goal is to connect all vertices while keeping the total cost as low as possible. Imagine that the company wants to connect several branch offices using network cables. If the company chooses connections randomly, the installation cost may become very high. Instead, it would prefer a solution that connects all offices while spending the minimum amount of money. The minimum spanning tree provides exactly that solution. This concept is used in many practical systems, including transportation planning, telecommunication networks, electrical wiring systems, and pipeline construction. Finding the MST efficiently is the main purpose of Kruskal's algorithm. Kruskal's algorithm is a greedy algorithm developed by Joseph Kruskal in 1956. It is specifically designed to find the minimum spanning tree of a weighted graph. The algorithm follows a greedy strategy. A greedy strategy means making the best available choice at the current step. Instead of examining every possible spanning tree, which would take a very long time, Kruskal's algorithm builds the solution gradually. It starts by examining all edges and sorting them according to their weights. Then it selects the edges with the smallest weight. Before adding an edge, the algorithm checks whether the edge creates a cycle. If no cycle is formed, the edge is added to the solution. If the cycle is created, the edge is rejected. This process continues till all vertices are connected. Because the algorithm always selects the smallest available edges, it usually reaches the optional solution efficiently. This makes Kruskal algorithm one of the most widely used minimum spanning tree algorithms. Now let's discuss the complete working procedure of Kruskal's algorithm step by step. The first step is to identify all edges in the graph. Next, we sort all edges in ascending order based on their weights. After sorting, we begin selecting edges one by one starting from the smallest edge. Whenever we select an edge, we must check whether adding it creates a cycle. If the selected edge does not create a cycle, we add it to the minimum spanning tree. If it creates a cycle, we ignore it and move to the next edge. This process continues repeatedly. As more edges are added, different parts of the graph gradually becomes connected. Eventually, all vertices become connected through selected edges. Once all vertices are connected and the spanning tree contains n-1 edges, the algorithm stops. The result is the minimum spanning tree with the lowest possible total weight. The most important idea to remember is that the algorithm always chooses the cheapest valid edge available. This example will help us understand exactly how Kruskal's algorithm works in practice. Consider a graph connecting four vertices A, B, C, and D. The edges and their weights are A to B equals 1, C to D equals 2, B to D equals 3, and A to C equals 4. The first step is to sort all edges according to their weights. After sorting, the order becomes AB with weight 1, CD with weight 2, BD with weight 3, AC with weight 4. Now we begin selecting edges. The first edge is AB with weight 1. Since this is the first edge, it cannot create a cycle. Therefore, we add AB to our minimum spanning tree. The total cost is now 1. Next, we examine CD with weight 2. Again, no cycle is formed because C and D are not connected to any other selected vertices. So, we add CD. The total cost becomes 1 plus 2, which equals 3. Next, we examine BD with weight 3. This set connects the group containing A and B with the group connecting C and D. Adding this set does not create a cycle. Therefore, we accept BD. The total cost becomes 1 plus 2 plus 3, which equals 6. At this stage, all 4 vertices are connected. Since all vertices are connected, the minimum spanning tree has been formed. The final MST contains the edges AB, CD, and BD. Notice that we did not select AC with weight 4. Why? Because all vertices were already connected before reaching that edge. Adding AC would create an unnecessary connection and increase the overall cost. Therefore, Kruskal's algorithm correctly rejects that edge. This example demonstrates how the algorithm always chooses the smallest valid edge while avoiding cycles and minimizing total cost. Now let's see what are the applications for this Kruskal's algorithm. One reason Kruskal's algorithm is important is because it has many practical applications in the real world. The first application is computer networking. When connecting multiple computers, routers, or servers, organizations want to minimize the amount of cable used while maintaining connectivity. Kruskal's algorithm helps achieve this objective. The second application is road construction. Governments often need to connect cities through roads while minimizing construction costs. The minimum spanning tree provides the most cost-effective solution. The third application is electrical power distribution. Power companies must connect different locations using electrical lines while reducing installation costs. Another application is water supply systems. Engineers use similar optimization techniques when planning pipelines that connect multiple regions. Telecommunication networks also use minimum spanning tree concepts when designing communication infrastructure. These examples show how a theoretical computer science algorithm can solve practical problems affecting millions of people. Now let's talk about the advantages and disadvantages. Kruskal's algorithm offers several important advantages. The first advantage is simplicity. The algorithm is easy to understand because it follows a straightforward approach of selecting the smallest edge available. The second advantage is efficiency. Instead of checking every possible spanning tree, make smart decisions step by step, reducing computational effort. The third advantage is that it always produces an optimal minimum spanning tree when the graph is connected. This means we can trust the result to provide the minimum possible cost. Another advantage is its usefulness for sparse graphs. Sparse graphs are useful that contain relatively few edges compared to the number of vertices. Kruskal's algorithm performs very well in such situations. Finally, the algorithm has many practical applications in engineering, network, transportation, and infrastructure planning. Because of these benefits, Kruskal's algorithm remains one of the most commonly used graph algorithms. Then, let's talk about the disadvantages. Although Kruskal's algorithm is powerful, it also has certain disadvantages. One disadvantage is the need for sorting. Before the algorithm can begin selecting edges, all edges must be sorted according to their weights. For graphs containing many edges, the sorting process can take time. Another disadvantage is cycle detection. The algorithm must continuously check whether adding an edge creates a cycle. For large and complex graphs, cycle checking can become challenging. Kruskal's algorithm may also be less efficient for dense graphs. Dense graphs contain a large number of edges, making the sorting process more expensive. In some situations, alternative algorithms such as Prim's algorithm may perform better. Therefore, while Kruskal's algorithm is effective, choosing the best algorithm often depends on the characteristics of the graph being analyzed. To summarize today's presentation, we began by learning about graphs and weighted graphs. We then discussed spanning trees and minimum spanning trees. After that, we introduced Kruskal's algorithm and learned that it is a greedy algorithm used to find the minimum spanning tree. We studied the step-by-step procedure of the algorithm, including sorting edges, selecting the smallest edge, checking for cycles, and building the minimum spanning tree. We also worked through a practical example to see the algorithm in action. Finally, we explored its advantages, disadvantages, and application. Kruskal's algorithm is a powerful optimization technique that helps connect all vertices while minimizing total cost. Because of its efficiency and practical importance, it remains one of the fundamental algorithms in data structures and algorithms. Thank you for watching this video on Kruskal's algorithm. I hope you understand the concepts of minimum spanning trees and Kruskal's algorithm. So, thank you once again for watching.